Hey students, I promised, particularly you in-person ones, that I'd go ahead and look at the examples that I would like to do for the first two sections. And it looks like there's 1, 2, 3, 4, 5, 6 that I like to do. And since we didn't get a time in class, I thought I would indicate which ones I've already done in some video lectures and then do the rest. And it looks like the first three, number 4, 5, and 8 from chapter 30, I'm starting to make this message to send it out on Canvas, that number 4, number 5, and number 8, and here are the different timestamps, are found in the video lecture number 20 for this class. And number 10 and number 21, that's 10 and 21, are found at the beginning. And here's the timestamps of the two, but are found here on video lecture number 21. So particularly for you in-person ones, you ones online, I trust you've already watched these video lecture. And so you've seen these 5, you just haven't seen example number 9. And so you guys who are in person, please go to the video lecture and watch these 5. But then also, here is the last one in my list, number 9. So let's do number 9 here together on this video. And that should give you 6 examples from these first 2 sections as you prepare for the exam here. So number 9 says this, that you have one long wire that carries 30 amps. Okay, so I have a grid here. And this long wire carries 30 amps to the left along the x-axis. So let me just kind of draw the x-axis. Maybe I'll put a little arrowhead here, and I'll put right next to it 30 amps. And then it says there is a second long wire that carries 50 amps to the right, and it's at this position, y equals 0.28 and z equals to 0. So calling the vertical axis the y, if I come up to some point, how about 0.28 meters, and draw a line that represents y equals 0.28, and then it's in the plane, z equals 0. And I can then put a little arrowhead here also, and say I have a current here of 50 amps. Okay. And maybe I'll refer to this as current number 1, and this one is current number 2, and we have our different amounts of currents. Okay, now to the first question, it says, where in the plane of the 2 wires is the total magnetic field equal to 0? All right, well, let's talk magnetic field. Let's, again, color code it with the green. If I do what we've been calling right-hand rule number 2, I can take my right hand and grab the wire. And so let's just grab wire number 1 with our right hand, with our thumb going in the direction of the current. And you can see your fingers are arcing around in kind of this fashion here. That means in all the spots above wire number 1, it's going in. And then all the spots below wire number 1, the field is coming out. And so it circles around it. So going in will represent with an X. And so all these spots that are above wire number 1, the magnetic field goes in. And then below, we will represent with a little dot, the field coming out. And to also indicate that this is coming from wire number 1, I'll put a little sub 1 under all of them. Okay, now we can do that same logic for wire number 2. Take our right hand, thumb in the direction of the current, pretend like we're grabbing it. You'll see our fingers kind of arc around. So that means above the wire, the field is coming out. And below the wire, it's going in. And again, maybe same logic. We ought to put a little sub 2 to indicate this is the field from number 2. And of course, then the total field, we've got to combine the two fields together. Because this is it. It says, where in the plane of the magnetic field equal to 0? And as you can see, between the two wires, the magnetic field is in the same direction for both these wires. And the only way you can get 0 total field is if the fields are in opposite directions and they are equal in magnitude. And so that means this space between the wires, we will never get 0 field. Here, they're in the same direction. There's no chance of it. But above the two wires, and for that matter also below the two wires, we can see that the field from 1 and 2 and 1 and 2 are opposite. And so if we can just get them the same magnitude, they would cancel off. And if we talk about above the two wires for a moment, you will see that pick any point up here. Well, how about I just call this point P here? Point P is closer to wire 2 than it is to wire 1. And this wire 2 has a greater current. So because of that, at any point above the two wires, the field coming from number 2 here, so like this one here, is always going to be greater than the magnitude of the field from number 1. So they may be in opposite directions, but they're never going to be equal up here. And so because of that logic, we can say we're never going to get them to cancel up here above the two wires. Our only chance of getting them to cancel is then below the wires. And you can see it is quite possible, and very possible, in fact, even likely. And so we'll see that there is a solution here, because somewhere down here, and again, if we call this some point P down here, you can see that the field coming from number 1, this pointing out, is closer than the field from number 2. And again, this closeness could give us the possibility of getting the same strength as the one that is further away, but has more current in it. And that's really the key. So there is a very likely chance, and I'll put it in black, that there is some kind of line here, some distance down, let me call it y, and technically that's a negative distance, so let me just, in terms of magnitude, some value below this first wire, with the negative values of y on my grid, where the field from the first one is equal in strength to the field from the second one. And we've already argued they're in opposite directions. So that's a good sign. And in fact, you can begin to see there's got to be a solution, because if you think about this line way down at the bottom, I'll just say miles and miles down, these are essentially the same distance away once you get a mile, because this is then, miles, or maybe I should say kilometers plus 0.28. And so way down here, there's not much of a difference in the distance between them, but this one has more current. So we're always going to get number 2 bigger than number 1 way down here. And then for positions that are really close to this 30, you can see that we're so close to the 30 that the field from the 30 amps is going to be way stronger than the field from the 50. So there must be some transition line right here. And that's what we're hunting for. What is that value of y where this field would be 0? Where in the plane of the two wires is the magnetic field equals to 0. So we can see that it's going to be this, some kind of line. So it's going to be, y equals something, z equals 0. Okay. So it's in the plane. I guess we don't have to say z equal to 0 because they say in the plane for us already. But we are going to have y equal. And it'll be some negative number. But let's talk about it in terms of a positive value for just a minute. All right, so if that conceptually made sense to you, let me go ahead and then do the calculation. Because then what I'm really saying mathematically here is the magnetic field of number 1 is equal to the magnetic field of number 2. And again, this is the strength of them because, as we said, number 1 is pointing out of the screen and number 2 is pointing into the screen in this area. But number 1 right here would be mu naught times the current in number 1 divided by 2 pi, and the distance away, well, from number 1 would just be this value of y. But the field for number 2 would be mu naught times the current in number 2 divided by 2 pi. And the distance away would be the absolute value of y plus 0.28. And that's because this wire's up here, and so the distance to this line is this y value, and then the other 0.28. And so now we have a nice equation that we just need to solve for the absolute value of y. And maybe just to save some nice calculator work, I'll cancel the stuff that's already there. Maybe I'll throw in then the 30. So this would be 30 over the absolute value of y. And this would be 50 over the absolute value of y plus 0.28. If I cross multiply here, I get 50 times the absolute value of y. And over here, I get 30 times the absolute value of y plus 0.28. And I'll write this as 30. And doing the distributive property, that's 30 times absolute value of y plus, and so here's where I need to find my calculator. But this is going to be 30 times 0.28, and so that's going to be 8.4. I'll leave the 8.4 alone and move the 30 over here, so that's 20 times the absolute value of y. And then finally getting the absolute value of y by dividing by the 20 here, and so 0.42. And so I guess to, again, answer A, it would be y equals negative 0.42, z equals 0, to represent the line down here. Okay, now let's keep going here. It says a particle with a charge of a negative 2 microcoulombs is moving with a velocity of 150, and this is in the x direction, and this is mega meters per second, along the line y equals 2.1. All right, well, let's see. Do I have any other different colors I can use to represent it? I do. I don't know if they'll stand out real differently. Let me grab my orange here. Not sure if the orange will stand out different than the red. Let's just see. Yeah. I guess it kind of does. I don't know how well it comes out on the screen. Okay, but let me find 0.1 on here. So it's probably about right there. So here's 0.1. And it is moving there's V. at this speed, but again, notice the I hat. So it's moving along the X direction, okay? Now, remember what we said earlier, that this area, which is now between the two wires, we have the fields going inward. So although we haven't calculated the strength of that field, and I think we're going to need that before this problem is over, but I would be able to say that the field at the location of this negative charge right here is going into the screen. And that's a big point to make here, because let's see, moving along there, calculate the vector magnetic force acting on the particle. All right, so let me call this page 1 and move on to page 2 here. And B then says the force equals Q V cross B. And V cross B, of course, is a vector cross product. So we're going to get out our right-hand rule for vector cross products. And we're going to be able to see what the force is. And that's what this whole thing says. And when they use this interesting word, calculate the vector magnetic force, they mean the force. That means its magnitude and its direction. So why don't I start with direction? Because direction means you need to take the cross product, then multiply by the charge, which remember is a negative number in this case, and that'll give you the force. So coming back to our picture, the velocity is to the right, the magnetic field is into the screen. So taking my right hand and first putting my fingers in the direction that it is moving, there's V, rotating my wrist so I can close it, I get V cross B, and V cross B then would be up in the Y direction. However, remember, it is some number, the charge, which is a negative number, times V cross B. So if V cross B is up, when you then multiply by a negative, you have the negative of up, which is down. And so the force is going to be some number and then in the negative J hat direction. Or maybe you can just say down if you want. But on this grid then, there would be this force down. Since again, V cross B with a negative makes it down. All right, so we got part of this problem done. We got the direction. Now we need to do this part here, which is its magnitude, okay? And so the magnitude of the force is Q times V times B times the sine of the angle between V and B. And so the easy part, if you will, and I'll just say, you know, this is the magnitude, is to put the 2 times 10 to the minus 6 coulombs. That's the amount of charge, a particle of this. And notice I don't even mess with the negative here since I'm doing the magnitude of the force. The velocity is 150 mega meters per second. That's what this was all about, 150 mega meters per second. And the magnetic field, I guess I still need to calculate that, so let's talk about that one. That's probably where a lot of work here is. And this area, we said we've got to add the two together. So I'll do that here in just a second. But I do want to put then sine of 90 degrees because, again, the velocity is then to the right and the magnetic field is into the screen, and that's 90 degrees. And so to finish this part B, I've got to find that field. And so I'm going to jump down to here and just say, okay, the total field, and certainly the magnitude of the total field, is the magnitude of the field from one plus the magnitude of the field from the other. And again, notice I'm adding them, and I'm adding them because I've already said they would be in the same direction, and they'd be into the screen, so I'm not going to call them a negative Z direction, but I'll just get its magnitude, okay? And so B1, or at least its magnitude, would be mu naught times I over 2 pi r, where our mu naught, of course, is our 4 pi times 10 to the minus 7. And for number 1, we would have current number 1, which is our 30 amps. And then we would be dividing by 2 pi. And the distance away is the 0.1 meters here from that line. And so we got 0.1. And that would give me the amount for field number 1. Now, I'll save myself a little calculator work and cancel off the pi's and reduce that 4 down to a 2. And so when I grab my calculator here, I can just go 2 times 10 to the negative 7, then multiply by 30, and then divide by 0.1. And so this is 6 times 10 to the negative 5 Tesla. And the same logic applies here for getting the magnitude of B, number 2. And so it's going to be this mu naught and current number 2. It's still going to be divided by 2 pi r. And so I'll go 2 times 10 to the negative 7 when I consider the mu naught and the 2 pi again. And so then I just need the current of 50. And I need the distance away. And since this wire is at 0.28 and the velocity of the charged particle is at 0.1, then this is 0.18 away. And so here I can do the 2 times 10 to the negative 7 times the 50 amps divided by the, 0.18, and I get 5.56, and maybe I should have put 6.00 for that one, times 10 to the negative 5 Teslas there. Okay. So when I put the two together here, I can just go 6 and 5 make 11.56 times 10 to the negative 5. So that's what I'll put up here, 11.56 times 10 to the negative 5. And so now, to answer B, I can put in the charge 2 times 10 to the negative 6 times 150 megameters per second times 11.56 times 10 to the negative 5. And so I get a force of 0.03, let's call it 4, one more significant figure, 7, and that would be in newtons. And of course, maybe I should have put here what a Tesla is, which is a Newton over a Coulomb per meter second, so that coulombs cancel off and meters per second cancel off, and we're left with newtons. So there would be the answer to B, calculate the vector magnetic force acting on the particle. And then C, what if a uniform electric field is applied to allow this particle to pass through this region undeflected? And of course, right there means net force is equal to 0. That's key here. Calculate the required electric field and vector electric field. So that means its magnitude and its direction. Okay, so maybe I'll call this page 3 here. Part C. But I hope you'll notice here that we calculated, and I guess I didn't really put it back up here, 0.0347. This is the magnitude and this is the direction, okay? And so the direction is downward, and we're going to then want to have an upward force. And so when it comes to electrical, the amount of force is Q times the electric field. And these are a little easier to work with, if you recall, because they don't have the cross product. And this just basically means that for a negative particle in this case, the force is negative or opposite of the electric field. So if we want our force to be upward to balance it, in other words, we want our force to be 0.0347 and in the positive j hat direction. That's the direction we want our electrical, because again, our magnetic is negative. And we want them to be equal in magnitude, opposite in direction, so that it can be undeflected. It can come out to be a net force of 0. Okay. Then you can see that we would want the field to be opposite of the direction of the force. So if we want the force to be upward in a positive y direction, which would be a j hat direction, we want this to be a negative. And sure enough, you can see that when you put in the charge. -2 times 10 to the, micro coulombs times our electric field. And by the way, notice in this case, I did not do the magnitude like I did so often with a cross product, where I get the magnitude of F is equal to this. And I just continue to leave it as a vector, which you can now see when you move the negative over to here does answer my point that the field will be in the negative j hat direction. And then I can get a number, and so there's the field. Let me just divide that by 2 micro, and we're looking at about a 17,000, I'll just round it to 300, and this force is in newtons, so newtons per coulomb would be my electric field. All right, well, I hope that was a good problem. It had a lot of nice, fun pieces, including this last part that kind of drew us back to some earlier chapters. But hopefully all that makes sense and is useful. Take care.